In today's lesson, we'll be talking about more multiplications of radicals along with division and rationalizing. So we're going to start right into binomials. If you have a binomial that has, or two binomials that have multiplication, you'll remember that we will use the acronym FOIL to help us with this. So that's just the process that we're going to do. We're going to do 2 times 1, which is 2. I will then do the outside, 2 times square root of 5. Now, because this 2 is outside the radical and this is inside the radical, you can't actually multiply them together. That's why the 2 goes on the outside. Then I'm going to multiply square root of 3 times 1, which is just square root of 3. And then finally, I'm going to do square root of 3 times square root of 5, which is square root of 15. Now, these are not the same radicands, so we can't put those together. And if I try to simplify square root of 15, I only get 5 and 3, and those aren't perfect squares, so that remains the same. So that's actually as far as I can simplify number 1. If we take a look at number 2, you'll see we'll have 2 binomials again with multiplication, so we'll FOIL. And when I go to multiply, we're going to get square root of t times square root of t. And this gives you square root of t squared, which is t. So what you should notice is if I multiply something by itself that's in a radical, the radicals cancel out and we just get that. So it's t. Then I'm going to go to the outer, which is minus square root of 5t. Go to the inner, plus square root of 5t. And finally the last, which will be minus 5, because those square roots cancel out. Now, what you will notice right away, hopefully, that's going to cancel. And you're going to get t minus 5. That's always going to happen when you have these types, okay? You have a plus and a minus when those are opposites. Those are called conjugates because those middle terms will always cancel out. And you're basically left with multiplying the first terms and the last terms. The main part of today's lesson is called rationalizing the denominator. And what we do with rationalizing the denominator is we basically don't like having radicals in the denominator. So it's called rationalizing because square root of 11 is an irrational number. And if you think about how you would divide that, it would be square root of 11 into 5. Well, 11's never ending, so we would actually never really be able to start this problem to divide it. So what we're going to try to do is get rid of that radical. And what you're going to do is you multiply by the square root if it's a monomial. So I'll multiply the square root of 11 over square root of 11. And the reason why this works, because example 1, or 2, numbers in the cancel out, and we get 11. Now, I'll get the 5 square root of 11 in the numerator, and you'll probably say, well, why is that okay? Well, you can have square root in the numerator because if I were to switch this around, 11 divided by 5 square root of 11. This is never ending, but at least I'll know exactly how many times the 11 can go into that estimated number as I start dividing. So let's look at number 4 and see if that needs to be rationalized. I have a fraction again, so I'm going to take the square root of 4 over the square root of 27y. That becomes 2, and the 27 is 9 and 3. So that's 3 square root of 3y. Now in this case, you'll notice there's a coefficient along with the radical. Again, I want to get rid of the radicals so to rationalize it, but I only need to use the 3y and not the coefficient. So I multiply by the 3y, and you get 2 square root of 3y over 3 times 3y. Again, because square root of 3y times square root of 3y cancel out to just give you 3y. We'll go ahead and multiply that and get 2 square root of 3y over 9y. let's look at a cube root. I'm going to do basically the same thing. I'm going to do the cube root of 1 over the cube root of 2x squared. Now in this case, if I multiplied by the cube root of 2x squared, 2 times 2 is 4, and I would get the cube root of 4. But that's not a perfect cube, and that wouldn't really help us out. So when you're dealing with cube roots, one of the easiest things I think to do is to look at the index and figure out how many you need. Well, I just don't need a second one. I actually need a third one. So I'm going to multiply it twice throughout. And what you'll notice then is when I go to multiply all these, 2 times 2 times 2, that's 8. And then x to the 6 over cube root of 4x to the 4th in the numerator. And the cube root of 8 is a perfect cube, so we're going to get 2. 3 goes into 6 twice. And then I'll simplify the numerator if I need to. 3 goes into the x to the 4th once, so I'll pull that out. But I can't do the cube root of 4, so I'll leave that the same. Remain 1x underneath. One of these x's will actually cancel out, and we'll get cube root of 4x over 2x as our final answer. Now technically, if you know right here that you just need one more x, you don't need to put so many x's in here when you're multiplying, but it usually helps just to stay consistent. Number 6 is a little bit different. You'll notice that we have 2 square roots in the denominator, and if I try and multiply by just one of them, and I distribute, I'd still be in a predicament of this right here of having square root of 6 and still having a radical. So we're going to think about what we did in number 2 and how those things canceled out and we got rid of the radicals. And we're going to use the conjugate. So if that is plus in the denominator, I'm going to use the opposite sign but keep everything else the same of the other two terms. So from there, I'm actually going to have to do quite a bit of foiling. I'm going to FOIL the numerator, so square root of 15 minus square root of 10 minus square root of 3 plus square root of 2. And because you should know what happens here, your middle terms will always cancel out. You really don't need to show that. And those other two terms should just cancel out and be 3 minus 2. And then our numerator we can't do anything with, and that's over 1. So this is actually going to be our answer because this reduces to 1. And our last example for this video. We have a binomial divided by just a single term, 16. I just want to make sure, I'm sure you guys know this already, but when you're dividing with a monomial, it divides into both parts. So I have 24 over 16 minus 36 square root of 7 over 16. Then I can reduce those individually. 8 goes into both of those, 3 over 2, 36 over 16, 9/4. And notice that it doesn't go into the radical, it's just the coefficient. So even if this was, let's say, 8, you don't reduce it. It stays that. It's only the coefficient in front of the radical. So we just simplify each term to reduce that.